Hey, ladies and gentlemen, we're going to talk about a sampling distribution of a statistic today. Okay, so when we do this, guys, I wanted to show you a class activity that I did last year. So I want to imagine if we're pre-pandemic, right? You're in my classroom with me and everyone's sitting in chairs, okay? And what I do is I ask you to get up, okay? Everyone stand up, find two other people and ask them how much sleep they got last night, including yourself. You write that down. Find the average of that and come report it to me, okay? Do this a couple more times. So come maybe do this 3 times for me. Okay, so I'm looking for, on average, how many hours of sleep are you guys getting? Okay, my population right now, I have this from last year, this is my 3rd hour statistics. And my capital N, that's my population size, I have 34 people. Now, here's what happened, right? Every time you came and reported that to me, I marked it on the dot plot here. So each one of these X's, erase this here, excuse me. Each one of these X's, that represents the average hours of sleep for lowercase n, so that's the sample size, 3 people. Okay, so that's what each one of these X bars represents. Now, we are on our way to a sampling distribution of a statistic. What is a sampling distribution of a statistic? A sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Whoa, lots of words, right? Okay, so let's get on and let's say, is this a true sampling distribution? Okay, and I say, is this the sampling distribution for X bar? So instead of saying sampling distribution of a statistic, I said sampling distribution for X bar. Why did I do that? I did that because each one of these X's, the statistic that I was interested in was an average, an X bar, okay? And I'm describing a sample there, and that's why it's a statistic. And that's gonna be in video number 2 that you're gonna watch. Now, you will be asked, is something a true sampling distribution of a statistic? And you need to know, why is it a true sampling distribution of a statistic? Well, let's look at this definition and see if what we have up here is a true sampling distribution of a statistic. And even before that, why are we interested in a sampling distribution of a statistic? We're interested in a sampling distribution of a statistic to draw conclusions about a population and make decisions based off of that conclusion, okay? So that's why we're interested in a sampling distribution of a statistic. Okay, so is this a sampling distribution of X bar? Looking at this definition here, a sampling distribution of a statistic is the distribution of values taken by the statistic. We have a distribution of values here. What is our statistic? X bar. So far, yes, we have a sampling distribution of a statistic. Now keep reading. It says, in all possible samples of the same size from the same population. There are 3 things here. Well, these all come from the same population. Each one of these X's here come from our population of 3rd hour stats. Same size. Yes, each one of these X's is an X bar. It's an average of 3 people. Each one of them. So same sample size of all possible samples. That means all combinations of size 3. Is this representing all combination of size 3 if I had 34 people in a class? Well, let's look at a calculator. I can show you. I can say, hey, I have 34 people. Let's find out how many combinations of size 3 I can get. You don't have to do this in your calculator. You don't even know how to do it, but I'll just show you now. Here's our combination button. So 34 people, we want to know how many combinations of size 3 would we get. So how many samples would we have up here? 5,984. We would need 5,984 X's up here in order for this to be a true sampling distribution of a statistic. So is this a true sampling distribution of a statistic? No, okay? And here's how we justify our answer. The graph is not the sampling distribution of it. What kind of statistic is it? It's X bar. In video 2, we'll talk about the different kinds of statistics that we have because it doesn't contain all possible SRSs, which is our combinations, of size 3, so from the population of 34 students. All right, well, ladies and gentlemen, this is a fill in the blank type question, okay? Star this, highlight it, whatever you need to do. More often than not, the graph is not a true sampling distribution, and they just want to know that you know why it's not, okay? So right here, we fill in what our statistic is, okay? Right here, we put in what is our sample size, our lowercase n. And right here, we put our capital N in context. So 34 students is what we had. What we can do though is we can make some claims about a population based off this simulation that we have up here, okay? And we're gonna just quickly review that right now. A newspaper claims teens nationwide get an average of 6 hours of sleep a night. Suppose one group of you had an X-bar of 8.4. Using the data above, what can they conclude about the claim that students get an average of 6? Let's actually, instead of saying 8.4, because no one had 8.4, let's say that looks like that might be 8.7. Okay, suppose one group of you had an 8.7. So we're going to pretend someone did, okay? Using the data above, or not pretend, I'm sorry, we're changing it just to work with our data a little bit more. Okay, using the data above, what can they conclude about the claim that students get an average of 6 hours of sleep a night? Okay, well, first of all, let's just think about this. Right now, people are claiming that students get an average of 6 hours of sleep, but you guys had a group where you had an average of 8.7 hours. Right away, there's a difference there. As a statistician, now we're wondering, is this enough evidence to refute this claim? To say, hey, we have some evidence that 6 hours might not be the truth. Or is it just natural variation? Okay, for example, if I flip a coin 10 times or 100 times, let's say 100, 48 of those times I could flip heads. Do I have a weighted coin, an unfair coin? No, it's just natural variation. But what if I flip it 100 times and 90 of those times I flip heads? Well then, hey, that's pretty far off of the truth. We might have some evidence to refute that the coin is actually a fair coin. Let's move on. Let's say, well, how do we do this? How do we conclude about a claim based off some evidence? The first thing that we want to do is we want to say, how many have that X-bar or more extreme? Or how many have that statistic or more extreme than that statistic? And 8.7, there's only one that is that value or more extreme than that, okay? So 1. How many trials total? How many trials total? That's going to be 38. Because there's 38 X's up there. Find the proportion. That means take this 1 divided by 38 every time when you're doing this, okay? If you follow my steps. 1 divided by 38 is approximately like 0.2. Or 0.02, excuse me. Approximately. Now what we want to do is we want to say, is this an unlikely event? This 1 out of 38, is that unlikely or not? Based off of the simulation, based off the data that we have up here. If we have an unlikely event, we have evidence against the claim. We have evidence to refute it. If it's not unlikely, we don't. Okay, it is just natural variation, like that flipping of the coin. We've talked about an unlikely claim right now for class. Our benchmark is something has to be less than 5% in order for it to be unlikely. If something is greater than or equal to 5%, it is not unlikely, and we have no evidence to refute that claim. It's just natural variation. That happens. Well, 0.02 is 2% if we change it to a percentage. So we have an unlikely event. That shouldn't have happened, right? Okay. What do we say then? Based off my simulation, the probability of getting an X-bar of 8.7 or more extreme is so low. We can just talk about this as being very low. That we have evidence against the claim, okay? We have evidence to refute that claim, and that's all I need from you right now. We have evidence that is pretty big. We can refute that claim. It's not just natural variation. Let's predict what would happen if I had 500 more trials. Well, what would happen if we had 500 more trials is the law of large numbers is going to take place. And I have that actual definition in the next video, but I'll just quickly talk about it. As we increase our trials, our experimental probability, okay, approaches our theoretical probability. So what the truth is about that population parameter. So it's going to stack up around the truth. As trials increase, the dots will start to stack up around the center, stack up or center around my population parameter. Again, what I just said, the truth. And that's all I have for you guys right now. This is just our intro to sampling distribution of a statistic. You're going to watch one about the videos, and then we're going to talk about the model, and that's where the fun stuff really happens.